Morning, everyone. So, taking a look at the syllabus, we are into this last module, which is the analog and digital optical transmission systems. We have covered the link analysis, system design considerations for point-to-point links, noise sources in optical communication, system architecture. I'll just take a look at what all we can cover under system architecture. And WDM is something which I think I've not covered. I might have mentioned it, but yeah, we'll be going through WDM, coherent optical systems. Then under methods of modulation, okay. We'll take a look at those later. So today, what I had thought about was, we'll start with optical amplifiers. Okay, so this is about optical amplifiers. Am I audible?
Yes, sir.
Okay, so there is something called as a repeater, and there's something known as an amplifier. So repeaters are also a kind of amplifiers, but not exactly an amplifier. A repeater is commonly electronic in nature, and what it does is it does optical to electrical conversion. So there is an optical detector. There's an optical detector which would convert this optical signal into electrical signal, and then there are signal recovery circuits which would give the proper or get the proper shape, and there's reshaping, retiming, and reamplification of the electrical signal to match what was actually transmitted at the transmitter end. So once uh, the reshaping, retiming, and reamplification of the electrical signal is done, uh, it is again converted into optical form by using an optical source. So this is what an electrical or an electronic repeater does. Okay, so what I mentioned about is 3R repeaters: reshaping, retiming, and reamplification. When we think about optical amplifiers, the optical amplifier directly will not do any reshaping or retiming. What it does is it will directly amplify the optical power which is coming at that point. I believe this is understandable. So most optical communication systems use the optical amplifiers because the electronic repeater becomes very it introduces delay into the uh, communication path, and it is also expensive. Okay, so to avoid these two, the optical amplifiers are a much better option. So there are many different types of optical amplifiers. So the most common optical amplifier which is used comes under the category of fiber amplifiers. And apart from fiber amplifiers, there are also semiconductor amplifiers which can be used. But normally in long haul optical communication systems, fiber amplifiers are what are used. So, uh, what should be the property or properties of a good optical amplifier? So, it should provide high gain, meaning it will add power to whatever is coming, and it should have a wide spectral bandwidth. So, this wide spectral bandwidth, this is essential for WDM systems wherein multiple wavelengths are transmitted over a single fiber. Okay, so when the amplifier has a wide spectral bandwidth, then all the wavelengths can be amplified. Uh, it should provide uniform gain over the amplifier spectral width. So, uh, so uniform gain refers to if I have a wavelength at 1300 nanometers and I'm transmitting information over 1300 nanometers, and I'm also transmitting information over say 1350 nanometers at two different wavelengths. So if my gain is of the order of around 50 dB at 1300 nanometers, and it is say 30 dB at 1350 nanometers, then the amplification is not the same for both wavelengths. It is different, and this can cause nonlinear effects to develop in the communication link. So that is something which is undesirable. So it's always preferable that whatever is the amplifier spectral width may be of something around 30 to 40 nanometers. So along that range of 30 to 40 nanometers or 50 nanometers, the gain should be uniform. It can be 30 or it can be 31 or it can be 29. So it does not vary more than 1 or 2 dB. So that is what is desirable. Uh, it's better if the amplifier can allow bidirectional operation, meaning when signals are uh, coming into the amplifier from both ends, then the amplifier should be able to amplify both signals. So it's highly possible that you have one wavelength at say 1500 nanometers in one direction and another wavelength at 1510 nanometers which is coming along the opposite direction. So this kind of bidirectional operation is desirable. And uh, noise, as we have seen earlier, noise is a thing which is undesirable, but you cannot completely remove it. So the lower the noise that the amplifier adds, better it is. So when we are transmitting multiple wavelengths, then whatever spectral width that the amplifier has, it will be better if there is no interference between multiple wavelengths, or because that can introduce crosstalk between the different wavelengths. So yeah, if uh, the signals which are coming into the amplifier, those are polarized in some form, then it is desirable that the that the amplifier should not be should not identify different polarizations and amplify them accordingly, but all polarizations should be amplified by the same gain. So it should be insensitive to polarization of the input. So the polarization can change along the length of the fiber. So if the amplifier is independent of the input polarization, then it will give better gain to the input signal. The insertion loss, whenever a component is inserted into a communication link, a loss is introduced in the link, because you should be having, because you must introduce some connectors, or uh, uh, means most likely connectors. So the connector can be a permanent connector or a temporary connector. So depending on how you want to use it, it can be a splice or it can be some SC or LC connector. So whatever connector that you introduce, so that should be introducing minimum loss. So lower the loss, better it is. Uh, Now, uh, the next point is, if my input power levels are very low, it is desirable uh, that I amplify them. Okay, but if the input power levels are not that low, even then I would like to uh, amplify it. Okay, but the gain must not be constant for all the input powers, because if the gain is constant, if I have an input power of say uh, of 1 microwatt and I amplify it to, let's say, 1 milliwatt, so I have a 1000 times increment in the power, fine, from 1 microwatt to 1 milliwatt. If the input is, say, instead of 1 microwatt, I get 100 microwatts, fine. Then in that case, if the gain is constant, if the gain is constant, then the output would increase 1000 times. So the output in that case would become 100 milliwatts, and 100 milliwatts of optical power is huge, and this can cause a lot of non-linearities will be introduced in the link. So it should not go to such high values, uh, but at the same time there should not be a maximum limit also, because if there is a maximum limit, then there is a possibility that some information might be lost. So there has to be a balance of the gain depending on what is the input power level. So it has to be adaptive. Then only you can have a good amplification. And all amplifiers need a pump source. Uh, uh, as we go ahead, we'll come to what is a pump source. So it is desirable that the pump source, this is an additional source, additional laser source, which is used with optical amplifiers. So it is better to have a small and compact one. And yeah, it's good if the conversion efficiency is good, meaning the power efficiency of the amplifier should be good. So this erbium doped fiber amplifier is the most common type of amplifier, or common type of fiber amplifier which is used in optical communication systems. And this is usually a fiber which is doped with a rare earth element. So usually it is erbium which is doped, but apart from erbium, holmium, neodymium, samarium, or ytterbium can also be used as dopants in optical amplifiers. So if you look at the name itself says erbium doped, right? So this was the first fiber amplifier which was found and which has been in use since a very long time. So, what is the most basic reason of using erbium? Because one of the transitions of erbium is at a wavelength of 1.55 micrometers, which also corresponds to the lowest loss in an optical fiber. So this is what is the basic configuration of using an erbium doped fiber amplifier. You have an input signal which is coming from a very long distance, could be some 100 kilometers or so, and after 100 kilometers this is put through a wavelength selective coupler. So this wavelength selective coupler will allow both these uh, this input optical signal and just give me a minute. Hello. Yes. Uh-huh. Uh-huh. Oh, sorry for the interruption. Yeah, my screen is visible, right?
Yes, sir.
Yeah. So apart from this optical input, there's also another optical input which is known as the pump signal. So what this erbium doped fiber amplifier does is it transfers the power of this pump signal onto this optical input. And you should mark here that the wavelength of this pump signal is different from the wavelength of the optical input. So usually, as we have seen here, so 1.55 micrometer is what is the optical input here, and here I think it's about 1480 nanometers is the wavelength which is used here. So this both these wavelengths are transmitted onto a single port. Okay, so and once both the wavelengths are uh, propagate in the erbium doped fiber, then the um the power which is present at a wavelength of the pump signal, that is transferred to the optical input signal. And by this mechanism the wavelength of this optical input signal is amplified at the output. So this is the fundamental mechanism of how an erbium doped fiber amplifier operates. So what the erbium doped fiber does is it excites the erbium ions which are present in the EDFA. Those are excited by the pump photons, which are coming at an with an input of lambda p. Okay, and these excited ions produce population inversion. And when the optical signal of wavelength lambda s passes through this EDFA, then stimulated emission is triggered, and and the de-excitation of the erbium ions causes an emission at a wavelength of lambda s. So this is how this is a simple setup, but it is slightly more complicated than what is shown here, because even if most of the power from lambda p is transferred to lambda s, some of the power in lambda p remains at this point. So that is an undesirable signal which should not be transmitted onto the optical fiber. So there should be filters at the output port which will block that particular uh, wavelength and allow lambda s to pass through. So this is the operating principle of EDFA. So you can see here, this is the pump band. So yeah, so you can have 980 nanometer 980 nanometers pump can be used, or a 1480 nanometer pump can be used. So there are two pump wavelengths which can be used. So there are different energy levels, as I had explained when I was discussing about lasers. So there are different energy levels which are present in the erbium doped fiber. So these erbium ions absorb wavelength of 980 nanometers and 1480 nanometers. So you can use either one. It can be 980 nanometers or it can be 1480 nanometers. So any one of these wavelengths can be used to excite the erbium ions. So whatever is the excitation, so there is a relaxation if the 980 nanometer wavelength is used for excitation or for pumping, then it goes to a pump band and there is relaxation to a metastable band. So from the metastable band to the ground state band, we always have an emission of 1.55 micrometers or 1550 nanometers. So if you look at this, 980 nanometers is smaller wavelength, right? Which refers to a higher frequency. So the energy associated with this absorption is much higher than what you have for this. And because of this, what is more popular now is uh, excitation using the 1480 nanometers, because this is more energy efficient. Okay, using 1480 nanometers in as a pump in optical amplifiers is a more energy efficient mechanism than using the 980 nanometers pump. Fine. So this is what is explained here. So what are the advantages? Uh, the concept is similar to that of what we have in lasers. In case of lasers, we need a fabric cavity which induces multiple reflections inside the cavity. Whereas these amplifiers do not need any cavity. Just as the optical input signal and the pump signal propagate along the EDFA, power is transferred from the pump to the signal. So this, since the principle of this fiber amplifier is very similar to that of lasers, this erbium doped fiber is also being used uh, to fabricate erbium doped fiber lasers. So that is also work that some are doing, and Um, in the near future, it's possible that the semiconductor lasers may be replaced by these erbium doped fiber lasers. So, uh, if you look at the advantages, you can see what is written here. It's inline amplification of the optical signal without requiring much of electronics. It's saying without requiring electronics, but we do need electronics at least to generate this pump wavelength. At least to generate this pump wavelength of 1480 nanometers, you do need a source. So a source would need a driver and all that. Uh, this provides high power transfer efficiency from pump to signal power, and the gain is relatively flat over the desired frequency band around 1550 nanometers. So these are the advantages of using an EDFA. Of course, so this point does what this point has is showing is not mentioning one important aspect, that if you use electronics with inline, meaning inline electronic amplification, then there'll be a lot of delay introduced because of the electronic processing. So that is eliminated when we use EDFA. So there are problems also with EDFA. As you can see in the figure here, uh, the left graph shows what is the input and the right graph shows what is the output. So when we have a weak signal, could be of the order of maybe 1 or 2 microwatts. So this 1 or 2 microwatts would be amplified to a very large level of something around, say, 1 milliwatt. But along with this 1 milliwatt, there will be additional wavelengths which will gain some power of the order of maybe some 1 or 2 microwatts. So uh, this is what is amplified spontaneous emission noise. Okay, and this is very broad. Uh, so it's not a desirable condition, but when the input signal is very weak, then this is a possibility. Uh, Another problem is that the amplifier gain can be saturated if the input is, let's say, of the order of some 100 microwatts. So it's a decent input power. So when we have 100 microwatts at the input, then the power which it can transfer to the wavelength of 1.55 nanometer would be limited to something around uh, from 100 microwatts, it will go to maybe 5 milliwatts or 10 milliwatts. It may not go to a desired level of 30 times or 20 times. It may be, sorry, it may not be multiplied by a factor of 1000, and the multiplication factor may be reduced. So this type of saturation is also possible in uh, EDFA. So these equations show what is the overall power gain of the amplifier. So this is what is defined as the gain of the EDFA. You have so it's a ratio between what is the optical output power to the input optical power. Typical gain values are about 20 to 30 dB. So it's about 100 to 1000 times the input power. So this gain again is not constant. This depends on what is the length of the fiber and what is the pump power and what is the concentration of the erbium in the EDFA. So to get the best results, these are usually optimized during fabrication. So if you look at this graph, the x-axis shows EDFA length in meters. If you're pumping at, if your pump power is of the order of 3 milliwatts, then you have a very high gain of 5 dB, okay, at a length of something around 3.5 meters or so. Okay, so beyond 3.5 meters, what happens is the gain falls. Your gain reduces. Okay, so if it is something around 6 meters, then the gain is maybe something around 2.5 or 3 dB. So you can see how it changes. Now, if the pump power is increased, then the gain is close to 10 dB. For 5 milliwatt pump power, it is close to 10 dB at a length of about 5 meters. So as you increase the length of the fiber, the gain falls again. Okay, so you can see here from this graph that even at a pump power of 7 milliwatts, if you have a length of about 6 meters, you're getting the maximum. Beyond a length of 6 meters, you're not getting additional gain. The gain is limited. So if you increase the pump power even higher, then you can have another graph, but the length would also not be increasing that much. Okay, uh, so depending on what is the pump power that you are going to use, you should be choosing the length of the uh, EDFA such that you can have maximum gain. Another thing that you need to consider is on the x-axis here it is given input pump power, and on the y-axis you have gain, and as you vary the length you can see how the gain varies. Uh, so up to 5 dBm of input pump power, it's almost the same. Uh, it's almost the same gain, but as you increase the pump power for increased length, then there is a factor of about 5 dB change in gain for every 1 meter. So this is a typical spectrum of how the EDFA would amplify the input signal. So this is the gain along the y-axis and the wavelength along the x-axis. So you can see here that at about 1530 nanometers, the gain is maximum of the order of nearly 30 dB. And as you go to higher wavelengths and also at lower wavelengths, the gain is falling. Okay, so this is not exactly a very desirable um, gain spectrum, but yeah, over quite a large band from say 15, 20, something around 15, 25 or so, up to 15, 55 or 1560, you get a gain more than 20 dB. So 20 dB refers to an amplification by a factor greater than 100. So that is a very good gain factor, 20 dB. So the wavelength range is almost of the order of around 30 nanometers. Okay, uh, it's not 30 nanometers, it's about 40 nanometers, from 1525 nanometers to 1565 nanometers. Okay, and this is what is known as the conventional band in optical communications. Uh, so if we look at the L band or the long wavelength band from 1570 to 1610 nanometers, the EDFA can be used for these wavelengths also, but in this band, the gain that we get is lower. As we can see here, um, beyond 1560 nanometers, the gain falls to something around maybe around 10 dB or so, which would reflect to a gain factor of around um, 10 or so. So the EDFA is also associated with noise, and you can see how the noise figure plays a role along with the gain spectrum. The noise is also a very critical part of this amplifier, and the noise figure, the unit of the noise figure, it's just a um, it's a ratio of what is the output signal power to the noise power. So this ratio is around 4 to 5. Okay, this is what is along the right side of the y-axis. That is the noise figure. So this can be used for WDM communication also. That's what is the meaning of this. Uh, it is desirable to have gain flattening. Gain flattening means here we have a high gain of the order of almost 30 dB at a wavelength of around 1530 nanometers. But when we come to 1540 nanometers, the gain is of the order of around 24 to 25 dB. And as we go up to 1555 to 1560 nanometers, the gain is of the order of 22 to 20 dB, right? So in order to flatten the entire gain spectrum, a wavelength filter can be used as is given here. So if this is the input, we can use the erbium broad fiber amplifier and get the amplified signals. And we can see that at 1530 we have high amplitude uh, output, and at 1540 and 1560 the optical power is lower. So a wavelength filter can be used which can reduce the powers at 1530 and 1540 and make it uniform over the entire band. So this would be the transmission spectrum of the wavelength filter such that uh, when this is superimposed on the signal, this is what you can get. So this is what is known as gain flattening of the amplifier. So there are other methods of gain flattening also. So controlling the erbium doping concentration is one method because this will not need to have. Hello. Class open day. Class open day. Okay. So this is about the gain flattening. So if the property of the fiber amplifier is or the fabrication process itself is optimized to have gain flattening, then this technique is referred to as intrinsic gain flattening. So this is about erbium doped fiber amplifiers. Any queries? If no one is having any queries, you can leave.